Section 1.3, Properties of Cloud-Native Applications. The scene is set. You are in the cloud. How should you design applications to take advantage of its characteristics? The CNCF identifies 5 main properties that cloud-native applications should have: scalability, loose coupling, resilience, observability, and manageability. Cloud-native is a methodology for building and running applications that exhibit those properties. Cornelia Davis sums it up by stating that cloud-native software is defined by how you compute, not about where you compute. In other words, the cloud is about where, and cloud-native is about how. I have already covered the where part, the cloud. Let's go ahead and explore the how. For a quick reference, Figure 1.4 lists the properties with short descriptions.
Figure 1.4. The main properties of cloud-native applications.
Section 1.3.1, Scalability. Cloud-native applications are designed to scale, meaning that they can support increasing workloads if provided with additional resources. Depending on the nature of those extra resources, we can distinguish between vertical scalability and horizontal scalability. Vertical scalability. Scaling vertically or scaling up or down means adding hardware resources to or removing them from the computing node, such as CPU or memory. This approach is limited, since it's not possible to keep adding hardware resources. On the other hand, applications don't need to be explicitly designed to be scaled up or down. Horizontal scalability. Scaling horizontally or scaling out or in means adding more computing nodes or containers to or removing them from the system. This approach doesn't have the same limits as vertical scalability, but it requires applications to be scalable. Traditional systems would usually adopt vertical scalability in the event of increasing workloads. Adding CPU and memory was a common approach to enable an application to support more users without redesigning it for scalability. This is still a good option in specific scenarios, but we need something else for the cloud. In the cloud, where everything is dynamic and in constant change, horizontal scalability is preferred. Thanks to the abstraction levels offered by the cloud computing models, it's straightforward to spin up new instances of your application rather than increasing the computational power of the machines already running. Since the cloud is elastic, we can scale application instances in and out quickly and dynamically. I discussed elasticity as one of the main characteristics of the cloud. Computing resources can be provisioned and released proactively, depending on the demand. Scalability is a prerequisite for elasticity. Figure 1.5 shows the difference between vertical and horizontal scalability. In the first case, we scale by adding more resources to the existing virtual machine. In the second case, we add another virtual machine to help the existing one process the extra workload.
Figure 1.5. When you need to support increasing workloads, the vertical scalability model will add hardware resources to the computing node, while the horizontal scalability model will add more computing nodes.
As you'll see when we discuss Kubernetes, the platform, whether KAS, PaaS, or something else, takes care of scaling applications in and out dynamically. As developers, it's our responsibility to design applications that can be scaled. The big obstacle to scalability is application state, which essentially is a matter of whether an application is stateful or stateless. Throughout the book, I'll cover techniques for building stateless applications and enabling them to scale without issues. Among other things, I'll show you how to push the application state from Spring to data stores like PostgreSQL and Redis. Section 1.3.2, Loose coupling. Loose coupling is an essential property of a system where parts have as little knowledge of each other as possible. The goal is to evolve each piece independently so that when one is changed, the others don't need to change accordingly. Coupling and its twin concept cohesion have played an essential role in software engineering for decades. It's a good design practice to decompose a system into modules, modularization, each of which has minimal dependencies on the other parts, loose coupling, and to encapsulate code that changes together, high cohesion. Depending on the architectural style, a module can model a monolithic component or a standalone service, for example, a microservice. Either way, we should aim at achieving proper modularization with loose coupling and high cohesion. Parnas identified 3 benefits of modularization. Managerial. Since each module is loosely coupled, The team responsible for it should not need to spend much time coordinating and communicating with other teams. Product flexibility. The overall system should be flexible since each module is evolved independently of the others. Comprehensibility. People should be able to understand and work with a module without having to study the whole system. The preceding benefits are usually among those associated with microservices, but the truth is that you don't need microservices to achieve them. In the last few years, many organizations have decided to migrate from monoliths to microservices. Some of them have failed because they lacked proper modularization. A monolith made up of tightly coupled, non-cohesive components, when migrated, produces a tightly coupled, non-cohesive microservice system, which sometimes is referred to as a distributed monolith. I don't consider this a good name because it implies that monoliths are made up of tightly coupled, non-cohesive components by definition. That's not true. The architectural style doesn't matter. A bad design is a bad design. Indeed, I like the modular monolith term proposed by Simon Brown to increase awareness that monoliths can promote loose coupling and high cohesion, and that both monoliths and microservices can end up being big balls of mud. Throughout the book, I'll discuss some techniques for enforcing loose coupling in applications. In particular, we'll adopt a service-based architecture and focus on building services with clear interfaces to communicate with each other, minimal dependencies on other services, and high cohesion. Section 1.3.3 Resilience. A system is resilient if it provides its services even in the presence of faults or environmental changes. Resilience is the capability of a hardware-software network to provide and maintain an acceptable level of service in the face of faults and challenges to normal operation. When building cloud-native systems, our goal should be to guarantee that our applications are always available, whether there is a failure in the infrastructure or in our software. Cloud-native applications run in a dynamic environment where everything keeps changing and faults can and will occur. This cannot be prevented. In the past, we used to consider changes and faults as exceptions, but for highly distributed systems like cloud-native ones, changes are not exceptions. They are the rule. When discussing resilience, it's worth defining three essential concepts: fault, error, and failure. Fault. A fault is a defect that produces an incorrect internal state either in the software or the infrastructure. For example, a method call returns a null value, even if its specification mandates that a non-null value is returned. Error. An error is a discrepancy between the expected behavior of a system and the actual one. For example, due to the preceding fault, a null pointer exception is thrown. Failure. When a fault is triggered and results in an error, a failure might occur, making the system unresponsive and unable to behave according to its specifications. For example, if the null pointer exception is not caught, the error provokes a failure. The system responds to any request with a 500 response. Faults can become errors, which may provoke failures, so we should design applications to be fault-tolerant. An essential part of resilience is ensuring that a failure will not cascade to other components of the system but stay isolated while it gets fixed. We also want the system to be self-repairing or self-healing, and the cloud model can enable that. Throughout the book, I'll show you some techniques for tolerating faults and preventing their effects from propagating to other parts of the system and spreading the failure. For example, we'll use patterns like circuit breakers, retries, timeouts, and rate limiters. Section 1.3.4 Observability. Observability is a property that comes from the world of control theory. If you consider a system, observability is a measure of how well you can infer its internal state from its external outputs. In the software engineering context, the system is a single application or a distributed system as a whole. The external outputs can be data like metrics, logs, and traces. Figure 1.6 shows how observability works.
Figure 1.6. Observability is about inferring the internal state of an application from its external outputs. Manageability is about changing the internal state and outputs via external inputs. In both cases, the application artifact is never changed. It's immutable.
The observability engineering team at Twitter identifies 4 pillars of observability. Monitoring. Monitoring is about measuring specific aspects of an application to get information on its overall health and identify failures. In this book, You'll learn about the useful monitoring features of Spring Boot Actuator and integrate Prometheus with Spring to export relevant metrics about an application. Alerting visualization. Collecting data about the state of a system is useful only if it's used to take some action. When a failure is identified while monitoring an application, an alert should be triggered, and some action should be taken to handle it. Specific dashboards are used to visualize the data collected and plot them in relevant graphs to provide a good picture of the system's behavior. This book will show how to use Grafana to visualize data collected from cloud-native applications. Distributed systems tracing infrastructure. In a distributed system, it's not enough to track every single subsystem's behavior. It's essential to trace the data flowing through the different subsystems. In this book, you'll integrate Spring with OpenTelemetry and use Grafana Tempo to collect and visualize the traces. Log aggregation analytics. Keeping track of the main events in an application is critical to infer the software's behavior and debug it if something goes wrong. In a cloud-native system, logs should be aggregated and collected to provide a better picture of the system's behavior and ensure the possibility of running analytics to mine information from that data. Throughout the book, I'll talk more about logs. You'll use FluentBit, Loki, and Grafana to collect and visualize logs, and you'll learn the best practices for logging in a cloud-native context. Section 1.3.5, Manageability. In control theory, the counterpart of observability is controllability, the ability of external input to change the state or the output of a system in a finite time interval. This concept leads us to the last of the main properties of cloud-native manageability. Drawing from control theory again, we can say that manageability measures how easily and efficiently an external input can change the state or the output of a system. In less mathematical terms, it's the ability to modify an application's behavior without needing to change its code. This is not to be confused with maintainability, which measures how easily and efficiently you can change a system from the inside by changing its code. Figure 1.6 shows how manageability works. One aspect of manageability is deploying and updating applications while keeping the overall system up and running. Another element is configuration, which I'll address in depth throughout the book. We want to make cloud-native applications configurable so we can modify their behavior without changing their code and building a new release. It's common to make configurable settings like data source URLs, service credentials, and certificates. For example, depending on the environment, you may use different data sources, one for development, one for testing, and one for production. Other types of configuration could be feature flags, which determine whether specific features should be enabled at runtime. I'll show you different strategies for configuring applications throughout the book, including using Spring Cloud Config Server, Kubernetes config maps and secrets, and Kustomize. Manageability is not only about particular changes themselves, but also about how easily and efficiently you can apply those changes. Cloud-native systems are complex, so it's essential to design applications that can adapt to changing requirements regarding functionality, the environment, and security. Due to this complexity, we should aim at managing as much as possible through automation, which leads us to the last of the 3 Ps of cloud-native: practices.